All right, so today we're going to be talking about a new gas law, and this is going to be probably the most useful gas law that you're going to be using in the unit because it now brings into another unit that we haven't used, which is moles, right? And so moles is the primary unit of chemistry. It makes sense that we would need a gas law that includes moles. So first, let's back up a little bit and talk about what we call Avogadro's principle. So Avogadro said that as long as we have the same conditions of temperature and pressure, then the following relationship exists. And that is, in any mole relationship, if I look at this equation and I would read this as 1 mole of hydrogen plus 1 mole of chlorine forms 2 moles of HCl, then proportionally we can apply that to volume units. So this could be read as 1 volume H2 or 1 volume chlorine produces 2 volumes of HCl. This is not unlike in recipes for cooking, how you might say 1 part plus 1 part plus 2 parts. It's the same idea that these are all proportional, right? And that's what this funny symbol here means. It means proportional. Okay, so and as it turns out, that under conditions of what we call standard temperature and pressure, which is often abbreviated as STP, then the pressure is 1 atmosphere and the temperature is 0 degrees Celsius. So 1 mole always occupies 22.4 liters. This is what we call molar volume. So, whenever you see standard pressure, standard temperature, you are to use these values in your gas law, right? And that's just going to be something that's going to be known from this point on. Okay. So then, extending that, Avogadro's principle extends to the relationship between pressure and moles. And so the relationship is that if the number of moles increases, the pressure will increase accordingly. So this is familiar because we've seen this with the other relationships where if you were to change the number of moles, we could then predict the proportional pressure as long as the other conditions are constant. So, bringing them into the fold then, if we consider all of the simple gas relationships that we've seen, we've talked about Boyle's law, we've talked about Charles' law, we talked about Gay-Lussac's law, and now Avogadro's principle. Wrapping them all together, we end up with what we call the ideal gas law. And the ideal gas law then is made up of the variables that we have already mentioned before. We're bringing in pressure, we're bringing in volume, we're bringing in temperature, and we have a new value called R. R is called the universal gas constant, and it's highly specific. The value for R that you will be using is 0.0821, and it has very specific units. The units on R will be written as atmospheres times liters over moles times Kelvin. All right, so whenever we are using the ideal gas law and you're using all of these other variables, you must have your units converted into these units. The pressure must be in atmospheres, the volume must be in liters, the temperature must be in kelvins, and N is number of moles. So you need to have your amount of substance in moles. And then your value of R is going to be inserted here. So, in our new gas law, the ideal gas law, you see 5 variables. one of which does not change. The constant does not change. And just like any other algebraic equation, we can rearrange this, we can manipulate this to solve for whatever variable we need. So let's take a look at this first problem here. We've got a sample of oxygen, and we are given a temperature, and we are given a pressure, and we are given a volume. How many moles of oxygen are in the sample? So, because they're mentioning moles, temperature, pressure, and volume, we're going to be using the ideal gas law. And that's kind of the tip-off as to when you need to use the ideal gas law. Anytime there's an amount of a gas, so if moles or grams are mentioned, that's your clue that you're probably using the ideal gas law. Right? Because that's the only gas law that incorporates the moles. All right, so the question was how many moles are in the sample, so we're going to rearrange this to solve for n. So just simply dividing both sides by RT will isolate n, so the equation becomes PV over RT is equal to n. And now I'm going to make sure that my units are in the correct form before I substitute them in. So the pressure, 785 torr. I need to convert this to atmospheres, and the conversion is that there's 760 torr per atmosphere. 785 divided by 760, so 1.033 we'll call it for now. Okay, so that's my pressure. My temperature needs to be in Kelvin, so 273 plus 21.5, right? That which gives us 294.5 Kelvin. The volume has to be in liters, so 435 milliliters. To convert to liters, you're going to divide by 1,000 milliliters, so 0.435 liters. Okay, so I have the values I need. Let's go ahead and substitute. 1.033 atmospheres. I am carrying an extra sig fig there. That's okay. I will round when I'm done. The volume, 0.435 liters. 0.0821 liters, atmospheres, moles, Kelvin. And the temperature, 294.5 Kelvin. All right, so let's double check our cancellations. The atmospheres in the numerator cancels. The liters in the numerator cancels. In the denominator, the kelvins cancel, and so your unit that you have left is 1 over moles, which, remember of how we deal with fractions, it's going to be 1 times the reciprocal of the denominator fraction, which equals moles. So our unit is going to be in moles, which makes sense because that's what we were trying to find. So let's go ahead and calculate. So the answer, 0.0186 moles of oxygen, and that's the first answer. The follow-up question is how many grams would that be? Well, no problem. We just multiply by the molar mass. A mole of O2 is 32.0 grams. So we're looking at about 0.595 grams of O2. Okay, so we've just used the ideal gas law to solve for the amount of gas, the number of moles of gas. We rearranged the equation. We made sure the units were converted into the proper units. Again, those units are atmospheres, liters, Kelvin. And we solved for the moles, and we went one step further, and we converted that to grams. Okay. Now, in this example, we just solved for moles, but you can solve for any of the variables. Next question might not be about moles. Lots of problems on your homework sheet will have you solving for different variables. Okay, so now let's talk about derivations of the ideal gas law and how we can use it to solve for more things. So I'm going to add a page here just so I can elaborate a little bit more on how these equations were determined. So let's back up, or let's use this blank space here. Let's start from scratch. Here's the ideal gas law again. And remember from stoichiometry that in order to solve for moles, you would often take the mass in grams and you divide it by the molar mass. So, since the ideal gas law incorporates moles, and because you have moles solved for, we can do a direct substitution. Like so. And this is perfectly valid. This is still the ideal gas law. Now, to make this a little more user-friendly, let's just extend the line to make it clear what is where. Okay, so the usefulness of this variation of the gas law is that now I can go and solve for other things. So for one instance, I can take this and I can rearrange it to solve for the molar mass. If I multiply both sides by molar mass and divide both sides by PV, I will get this variant. So this is useful whenever we have the pressure, the volume, the temperature, and the mass of the gas. We will be able to solve for the molar mass using this version. Another variation is if I need to solve for density. If you recall, density from Unit 1 is the mass divided by the volume. Well, in this gas law equation, we have grams and we have volume. So the grams is this component right here, right there. So I can rearrange this to solve for grams over volume by multiplying both sides by molar mass, dividing both sides by RT, dividing both sides by V. And this will be our density, and it will be in the units of grams per liter. So if you need to solve for the density, you could go ahead and use this equation, and as long as you have the pressure, the identity, which will get you the molar mass, and the temperature. One more thing is that oftentimes in gas equations, density will be given. So for example, let's say that they tell you the density is 1.25 grams per liter. If they give you the density of a gas in a problem, what they are giving you is two values. That they are giving you both the mass and the value for volume. It's implied, but the value for volume is 1 liter. So what you would do is you would plug into the gas law 1.25 for grams and 1 liter for volume. And then this is presuming that you have the other variables. Then you can use this to solve for other things like the pressure or the molar mass or the temperature. All right, so let's say the question was, what's the molar mass of gas? All right. What is the molar mass of the gas at STP? Remember, standard temperature is 273 Kelvin, or 0 degrees Celsius, but we need it in Kelvin here. Standard pressure is 1 atmosphere. So if they want to know what the molar mass of this gas is under standard conditions, and they are giving you the density, we have everything we need. So for grams, 1.25, R, temperature, 273 Kelvin, pressure, 1 atmosphere. Now this pressure is It's not measured, it's defined, so that it says 1, but it's not really 1 sig fig. And volume, again, volume is implied, so that's defined, it's not measured, so don't think that's 1 sig fig. So the fewest sig figs we have here is actually 3. So when we go ahead and run the numbers, this gas would have a molar mass of 28.0 grams per mole. And just to make sure you understand how we got those units, let's take a closer look. All right, in the numerator, Kelvin and Kelvin cancel. We have liters in the numerator, we have liters in the denominator. We have atmospheres in the numerator, we have atmospheres in the denominator. So the only units that go uncancelled here are grams and moles that are in the denominator. So therefore your units will be grams per mole. So that's how you use the density in a problem if it's given. So let's try these two problems. Go ahead and pause the video while you work on these, and unpause it when you want to see me work through the solution. Okay, so let's start working through this. When we want to identify a gas, like in this problem here, generally you want to do so by finding the molar mass, right? Because finding the molar mass is one way that we can identify a gas. So in order to do that, we need to see the variables that we will need. So what do we have? We have grams. We have milliliter or volume. We have temperature. And we have pressure. And R really doesn't change. Okay, so we have what we need. We just need to make sure that we plug in the correct units, so we have to do some conversions. All right, so 300 milliliters, so the volume, 300 milliliters, liter is 1,000 milliliters, so really we have 0.3. That's not enough sig figs. Let's pretend there's a period there. So 0.300 liters, okay. Our temperature, 20 degrees plus 273, so 294, or 293, my bad, 300 Kelvin. 685 torr. We need this in atmospheres, so divide by 760. 0.901 atmospheres. And the mass was given. There's no need to convert the mass. It's already in grams. So let's plug in what we have. So okay, let's crunch the numbers. And we get 129 grams per mole. Remember, grams per mole is the unit for molar mass. Let's double check our unit cancellations. So Kelvin and Kelvin, atmospheres and atmospheres, liters and liters, and the only units left are grams per mole. So as far as what identity is this, what gas is this? Well, the clue says that this is an inert gas. Inert means non-reactive, and that typically means noble gas. So we would look to see what noble gas is closest to this, and the closest gas would be xenon, because xenon's mass is 131, and 129 is reasonably close to 131. So it's probably xenon. All right, let's look at the next problem. They're asking for the density, and they're giving us the temperature, they're giving us pressure, and they're giving us, inadvertently, they're giving us the molar mass. They're not directly telling us what the molar mass is, but they're telling us it's nitrogen, and you know the molar mass of nitrogen. So we can find the density. So again, we're going to take the ideal gas law, we're going to rearrange it to solve for grams over V. So if this is the substituted form of the gas law, PMM over RT is equal to G over V. Okay, let's do some converting. 65.5 degrees plus 273. This is going to be 338.5 Kelvin. 140 kilopascals. So an atmosphere is 101.325 kPa. .38 atmospheres. And the molar mass for nitrogen is 28.02 grams per mole. All right, let's go ahead and insert all of that. So, pressure first, molar mass, temperature, let's check our units. Kelvin, Kelvin, atmospheres, atmospheres, inverted moles and inverted moles. Our last units remaining, grams over liters. Okay, so 1.38 times 28.02 divided by 0.081 divided by 338.5. All right, 1.39 grams per liter. Okay, so let's recap and review. So Avogadro said that moles are proportional to volume. And there's what we call a standard temperature and a standard pressure. The standard temperature is 0 degrees Celsius, which is 273, and standard pressure is 1 atmosphere. If you plug these values into the ideal gas law, you end up getting 22.4 liters for the volume. So this is what we call molar volume. 22.4 liters is molar volume. The ideal gas law is a combination of all of the little gas laws. It is the most useful because this is the first gas law that allows us to solve for moles. All right, the trick is, in order for this to work, because of all these constants that this law is essentially a sum of, there's a value for R, and that has to be used every time you use this law. It's 0.0821, and it's highly unit specific. You must have these in the correct units if you're going to be using this number. Rearranging the ideal gas law, you can solve for any one of the variables. In this first problem, we had to solve for moles, right? And so we rearranged the equation. Rearrange the equation first, and then plug everything in, right? Don't try to plug it in as you do it, because you're likely to make a mistake, because halfway through you might realize you don't have something in the right unit. Okay, so convert your units, and then before you substitute them in. The ideal gas law can be used to solve for other things instead of, beyond volume, pressure, temperature, and moles. We can solve for things like molar mass and density. We just have to be a little creative with some substitutions. Take the formula for moles, insert it into the ideal gas law for moles, and that gives us PV is equal to GRT over MM. And from this form, we can rearrange to solve for either molar mass or density as well. Again, the same parameters apply. You need to make sure that you have your correct units. And we can solve for the molar mass and density, just like we did here.